Multiplexers are a very important circuit, okay, a very important logical component which can be used as multi-purpose. Okay, so in today's lecture, we'll actually look into how this can be employed for you know implementing different logics. So if you can understand just one section, okay, just one part, then it's going to be easy to implement the other logic gates. So we will see all of them today, and we will try and understand how these are used in an efficient way when we decide with the logical design of any circuit. A 2 raised to 1 input mux has n select lines. So as you all have seen, okay, you have a multiplexer, and this multiplexer, okay, your pass transistor, just like your pass transistor, okay, it will have something called a gate. Okay, so this gate is connected to a select line, okay, just like how you can see here. Okay, so here this is a diagram of a 4 is to 1 mux, okay, which has two select lines, which is S0 and S1. So when I have two select lines, it means I will have four combinations. Okay, so how we will go about with this is that, okay, you can see that your S0 is 0 because it's bar, S1 bar, 0 1 1 0, wherever it's a bar, okay, it's a 0 1 1. So these are going to be our uh, combinations for two input. Accordingly, you will be multiplying them with A, B, C, and D. Okay. So if I select 0 0, if I select 0 0, then A is going to be selected. If I select 0 1, okay, then B is going to be selected. If I select, if my select lines are 1 0, then it's going to be C. Okay. Similarly, if I select 1 1, okay, then the input line selected will be D. So ultimately, I will be using two 2 is to 1 mux. Okay, so individually, this is a 2 is to 1 mux. Okay. 2 is to 1 mux. Why is it called 2 is to 1 mux? Because, can someone unmute and respond? Why is it 2 is to 1 mux?
So two inputs and one output.
Correct. So I have two inputs here, and it's just giving me one output. So I can also think of, this is getting converted from parallel to serial. Correct. See, because I have lines in parallel here. Okay, AC is like parallel lines, but I'm just getting one output. So I can say that these are my parallel inputs, and the output that I'm getting is a serial output. So using one 2 is to 1, then you have another one here 2 is to 1 mux. Okay, and with the help of your select lines, okay, so what I'll be doing, I'll be combining them, and this is also another 2 is to 1 mux. Understood? Okay, so when you have 0 and 1, okay, as I told you, you will have four combinations. Okay, you have 1 1 1 0, okay, 0 1, and 0 0. So accordingly, you are going to get your Z equation. Any doubts till here, students? Till this point of time, any doubts? You can unmute and respond. Yes, can I continue, or any doubts here?
No doubt, sir.
Okay, fine. So this is how your mux is. Okay. So as I was mentioning, your select lines S, then your inputs A and B, then your outputs Z. So for 0, you can have 4 combinations. For 1, you can again have 4 combinations. Okay. So AB can be 0, 0, 0, 1, 1, 0, 1, 1. Okay. So when I select 0, okay, then only A is getting selected. Whatever is A, that is coming at your output. Okay. See, my selection here is 0. So which means I am selecting only what is in A. So what is in A comes and sits in your output. Okay. Next here, I can even give 1, 1. Now I have selected 0, which means it is only working out with A. So 1, 1 will come and sit here. Right. So based on your select lines, it's going to uh, replicate the output towards your replicate the output whatever is in your input. Right. So the other case here, whenever it is 1, then B is going to get selected. Right. So here you can see that 0, 1, 0, 1. So these two things are the same. Right. So that is why I have 1 here. So this can either be 0 or it can either be 1. So when it is 0, then A is getting selected. When it is 1, then B is getting selected. So this is very clear to all of you. Yes.
Yes, sir.
Okay. Fine. So now we will go ahead and understand how this implementation can be done with the help of mux and having different logical circuitries. So all the logical circuitries here can be implemented with the help of your multiplexer. Okay. Very important logical component that we'll be discussing. So we have 2 raised to n input mux and that will have n select lines. So these select lines are S0, S1, right? So if it has n select lines, then 2 raised to n will be the number of inputs. So if I have 2 select lines, say S0 and S1, then 2 raised to 2 will be the number of uh, combinations. Okay. Right. So let's move on. It can be used to implement logic functions by implementing LUT. LUT is nothing but your lookup table. So now, I think all of you would have seen Adobe Reader, right? A PDF document. So here you will have an option of jumping to a page number, isn't it? So in a document, if it has about 100 pages and you want to immediately jump to 95th page, is it possible or not?
Possible, sir.
Possible, right? So this is happening with the help of lookup table. So internally there is a table that gets created and it sits in the memory. Okay. So as soon as you search for something, so this table will actually look up for which number you are searching for. So not only the page number, nowadays you can even search for words in a particular document, right? Okay. A two input mux can implement any two input function. A four input mux can implement any three input function, and similarly it goes on, right? So two input, two input function, four input can implement any three input. Okay, then eight input mux can implement any four input function. This property of MUX makes FPGA implement programmable hardware with the help of LUT MUX. So this FPGA implementation will be, studied in detail in your next semester in the subject called HDL, Hardware Descriptive Language. So there is a separate section, okay, which talks about the FPGA implementation. Okay, so yeah, here I'm restricting the discussion only to the implementation of AND or NAND, NOR, XOR, and XNOR. Okay, so only these gates will be discussing, and these will be implemented with the help of two input MUX. Right, right. So the first one that we'll be looking into is AND gate. So the best thing that you can do is first, go ahead with the truth table of AND gate. So as we all know, A, B, so between 0, 0, 0, 1, 1, 0, 1, 1 is going to be the combinations. So since it's an AND gate, so you know the outputs triple zero, 1, right? So it will be a high only if both the inputs are high. If one of them are low, then consequently the output is going to be low. So that's the property of an AND gate. Okay. Now what you should do is you should compare the output. Okay, compare the output with the inputs. So now this truth table will give us a relationship between the inputs and the outputs. Yes or no? Do you all agree with that point? Yes. Truth table gives us a relationship between input and output. Is that
Yes,
true or not? Yes.
sir.
Yes. So I have my set of inputs and then I have my set of outputs. So it is trying to relate. If I give this combination, then what is going to be my output? If I give 1, 1, what is going to happen? So ultimately, it is telling me, okay, what kind of inputs and how is the corresponding output. So that is what you have to, uh, concentrate here. Now, what we should do is we should think of the next level. We should think how I can relate these numbers to A and B. Okay, how I can relate. So if you carefully see, okay, the output is equal to 0 when A is equal to 0. Yes or no? And the output is same as B when it is 1, when A is equal to 1, right? So what we can do here is, see what we can understand here. These are whenever A is 0, 0, output is equal to 0. Okay. So next here 0, 1, and your output is also 0, 1. Yes, can you see the relationship now between these binary numbers? So now, since I am depending my output based on A, so I will say that I will take A as my select node. So when A is equal to 0, okay, so I will be connecting this to, okay, because I need my output to be 0, right? So A equal to 0, this output should be equal to my input. So input is what? Ground. That ground I'm giving as output. Now when A is equal to 1, okay, so B should be my output. So B is here. So that will come and sit as my output. Students, were you able to understand what I'm trying to explain? Yes or no?
Yes, sir.
Okay. So I want to know, okay, with the output, what is exactly matching. So at output, I want 0. So my input, what is my input that replicates at the output is the relationship that I have to bring out here. So I will draw a mux, okay, and A is going to be my select line. And if 0 has to come here, then at my input, I have to take ground. Or you can connect instead of this, you can even put it as 0. 0 also can be done here, okay, instead of ground. So if you connect 0 here, when A is equal to 0, 0 will come and sit. If if A is equal to 1, see, when A is equal to 1, then B should be equal to output. B should be equal to output. So I will put B here and output. So there is a lot of thinking involved, okay, whenever you try to implement a mux. There is lot of research actually happening with multiplexers, with transmission gates, with fast transistors. Okay, are you aware that even with D flip flop, there is lot of research and development happening. It's a simple flip flop. Whatever is your input, the same thing is your output, but still there is a lot of research happening even in D flip flop. Okay, so you can imagine the level of complexity, the level of thinking that is involved for the implementation of mux. Okay, so that's why this mux and demux is a very special circuit, logical circuit, which not only helps us in selecting the inputs, but also it can help us in trying and getting the uh, logical circuits, logical gates implemented, multi-purpose, multi-purpose. So what you can do, first thing, have the truth table. Second thing is you can come up with these summary statements, and the third thing is come up with this mux and verify your mux with your statements in number 2. Okay, and of course this is going to be very simple. You can just represent it as your normal logic circuit. So here you can see out is equal to 0 and A is equal to 0. So this is only giving you the clues that you have to select A as your select line. Output should be equal to 0. So which means at my input also I should be having 0. Okay. So altogether, okay, I can say that this will help you. Okay, this will help you. These statements, step number 2 will actually help you in step number 1. Of course, all of you are very much aware, you can do it. Step 2 is getting these statements. Once you have got these statements, implementing that here becomes very easy. Do you all agree with me? Yes. Fine. Now let us move on to the next one. Okay, NAND gate. So similarly, what I will be doing is I'll be putting the truth table 0 0 0 1 1 0 1 1. Then I'll be taking my respective outputs. So it's going to be a inverted AND gate. 0001 1110. Yep. So that is going to be my output here. So now I have to come up with a relationship. Okay, output is equal to 1 when A is equal to 0. So again here what I can do, I can use my A as selector. Then output is equal to B. Okay, output is equal to B when A is equal to 1. Okay. 1 0 0 1 1 1 1 0. Okay, so yeah, output is
Sir,
equal
isn't
to,
it B complement?
output is equal to, yes, yes, B complement, correct. So output is equal to 1 when A is equal to 0. Okay, so we can again bifurcate here, when A is equal to 0 and when A is equal to 1, correct. So which means what I can do here, I can take A as my select line. Okay, so I'll take A as my select line, and I will say when A is equal to 0, A is equal to 0, output should be equal to 1. So since it is 1, what I will do, I will connect it to VDD, or you can connect it to high value. Anything is fine. Next, output is equal to, you can see that you have 0 1 here. Okay, but then you have a complemented version which is 1 0. So I will say it is equal to B complement. Okay, so A 1 B complement is equal to output. Okay, so a lot of thinking is needed in order to come up with step number 2, according to me. Okay, you have to really think, and you have to understand as to how I can bifurcate things. So when you have this kind of logical circuits, okay, you can divide them into two. So when I say divide them into two, when A is equal to 0, when A is equal to 1, okay, these kind of bifurcations can be done. Okay, so I hope this point was clear. I can move on to the next one, isn't it?
Yes, sir.
Okay, so now OR gate. So OR gate also, you can have the tabulation and relationship statements, implementation. So just have a look at it. So your output is equal to 1 when A is equal to 0. Then your output, okay, you can see that here also it is a complemented version. Here also it's a, yeah, oh yeah, this was NAND. Yeah, this is OR. So your output, okay, you can see here output is equal to B, right? Then when A is equal to 1, output is also equal to 1. So you have to see the truth table properly and understand how they are related. Okay. So I have 0 0 here. Then here I'm getting 0 1. So where is this 0 1? 0 1 is equal to B. Okay. Next, when A is equal to 1 1, okay, that is when A is equal to 1, okay, I am getting all ones at my output. So I can say that output is equal to always 1 when A is equal to 1. So this is like a condition when you all have written your programming, right? You're all aware with your programming. The same thing here. Output is so much when A is so much. Output is 1 when A is, so it's a condition there. If A is 0, then output is B. If A is 1, then output is equal to 1. So how do I implement it? I will take A as my select line because I have when A is equal to 0, when A is equal to 1. So A is going to be my select line. I put 0, 1 here. So 0 output is equal to B. So output should be equal to B. So B I will be giving as my input. Similarly, output is equal to 1. So I will either connect to VDD or I will connect to a high value. But so in general, if you want to put it, then you can mention as VDD. and later on you can put your logical diagram. Okay. So next, NOR gate. So in NOR gate, put your truth table. Once you have put truth table, then now is the time to understand how output is related to input. What kind of conditions that you can come up with. So when A is equal to 0, this is the complemented version of B. Okay, you have 0, 1, 1, 0. Next, when A is equal to 1, I can say output is always 0. Okay. The same thing here, when A is equal to 0, A is 0, I am putting B bar so that B bar will come here when I give A is equal to 0. So A is 0, B bar is selected, B bar comes as my output. Okay. So next, when A is equal to 1, 0 comes and it gets into the output line. So ground, as I mentioned, ground is a generic form. In fact, it is a 0. So output is equal to 0 when A is equal to 1. So two input NOR gate. So OR gate is there with a complement. Okay. So that is nothing but your N here, negated OR. Fine. So we have XOR, XNOR, and NOT. So XNOR, okay, we are going to come up with the complemented version of XOR version, right? XNOR. So if the inputs are same, it's actually 0 in XOR, but in XNOR, it is the complemented one. So if the inputs are different, you're getting a 0, 0, 1. Now try to see the relationship between them. So this is equal to B when A is equal to 1, and this is B bar when A is equal to 0. So A0, B bar, A1, B, A1, B. Okay. Next with XOR, if it is same 0, different 1. So XOR is a very important gate which can also act as comparators, right? When I say comparator, it can compare two values. It can see if the levels are same or not. Based on your output, you can decide, okay, A and B are same, but I do not know if it's 0 or 1. Okay. So that's the only downside. Because see, for 0, 0 also you're getting 0, for 1, 1 also you're getting 0. So here what conclusions can I draw? I can only draw that the inputs are same or different. That's it. Do you all agree with me?
Yes, sir.
Yeah. So I cannot say that, I'm getting 0 because A and B is 0. No, I'm even getting 0 here, even though A and B is 1. Right. So the last one we'll be looking into is NOT gate. So NOT gate is going to be very simple. 0, 1, 1, 0. So A is going to be my select line. When A is 0, what do I want? I want 1. So 1 I will put it here. When A is equal to 1, I want a 0. So 0 I will put it here. Okay. So in this way, Mux plays a very important role in getting the logical circuit implemented in implementing any kind of circuitry. So we can even take this to the next level by creating a different truth table, trying to find out the relationship between the outputs and the inputs, and trying to come up with statements. These statements can be mapped onto the multiplexer. Right? So you've got any doubts till this point we have discussed? Is it all clear? So do you think Mux is a very special component in logic design?
Yes, sir.
Yes, indeed, right? Okay. So we will be looking into few more concepts, okay, in our upcoming lectures, wherein we will dive deep into the concepts and discuss in detail as to how these circuits or the concepts are implemented.